All right, for part B, I'm going to have a similar analysis. Remember that x is a variable. In part B, I have also an alternation going on here, right? An alternation going on here. So, but still, I'm going to apply the ratio test. Okay, so essentially, an is going to be the full ratio here, right? Full fraction with the alternation. And what I'm going to look at is the limit of the absolute value of the ratio. Okay. So let's write this precisely. All right. So minus 1 to the power of n plus 1. Okay. X to the n plus 1. N plus 2. N plus 3. So this whole thing is a n plus 1. And I'm going to divide it by an, but an is another fraction, so we generally flip this over. So I'm going to flip an over. N plus 1, n plus 2, minus 1 to the n, x to the n. Okay? That is equal to, so let's see what cancels. So, well, before in fact the cancellation, maybe I can rewrite this real quick. So first of all, in fact, so this is minus 1 to the power of n plus 1. This is minus 1 to the power of n. Well, these are not really important in terms of this analysis here because I take the absolute value. Because these guys are plus minus 1, taking plus minus 1 values. But when you take the absolute value, all the negative signs are absorbed, right? Absorbed. So I don't need to include them in my analysis. What I'm going to do next, in fact, is just to split this term as x to the n times x. Okay, x to the n times x. And I'm going to cancel x to the n here. One x to the n here, another x to the n here. Okay? So let me just write down the simplified version. Again, alternation is gone. So you have n plus 1, n plus 2, n plus 2, n plus 3 left, as well as x. Okay, I sort of wanted to isolate x from the other terms because the limit is going to be on n, and x is just a parameter here. So you can get a scratch paper here, okay, and then think about the limit of n plus 1, n plus 2, n plus 2, n plus 3. In fact, there's also one more cancellation here, right? So if you have the top and the bottom coming with the same order of polynomials, right? So the limit is the ratio of the leading coefficients, or you can simply apply the L'Hopital's rule. So the limit is going to be here 1, okay? And you can put the absolute value if you want to. It's not going to change anything. So so speaking of that, going back here, this limit on n is going to be 1, so the whole thing is going to be what? The absolute value of x. Okay. So you can also add the limit here, but that doesn't change anything again. Just to be precise, let me just write that down here. But this is exactly equal to absolute value of x. Okay. The ratio says, ratio test rules that the limit has to be less than 1 for convergency. Okay. So this implies that the absolute value of x has to be less than 1. What does that mean? Well, absolute value of x less than 1 means x's are in between -1 and 1. Okay. So I got an interval, which is -1 and 1. That's good. This is the interval of convergency, but I have to analyze this also at the endpoints. So here I have 2 more steps to go. X equals -1 and x equals 1. So I have to rewrite the infinite series here for x equals -1 and x equals 1. So why don't we do it? So for x equals -1, the series look like -1 to the n, -1 to the n, divided by n plus 1, n plus 2. n plus 1, n plus 2. And the other one is, the other one is -1 to the n 1 to the n plus 1, n plus 2. Okay, let's try to simplify both series. Well, this is minus 1 to the n times minus 1 to the n, which is two exponentials with the same base. So it's you just multiply the bases, right? So it's 1 to the n, because minus 1 times minus 1 is, or you can add the exponents. You can write it as like minus 1 to the 2n if you want to, if that's easier for you. Okay, so that's minus 1 squared to the power of n. That's 1. What I'm trying to say is like the top is just 1, plus 1. Okay, so whichever way you handle, just please observe that the top is just 1. So it's 1 over n plus 1 and n plus 2. For this one though, 1 to the n is just 1. Okay, so the alternation is preserved here. Minus 1 to the n stays as is, as well as the bottom terms. Okay, so I have two different infinite series, and I can apply any test that we learned in the past, okay, to be able to handle these two infinite series. But for this one, probably I'm going to apply the alternating series test. And for this one, well, I can use the comparison test, I think. You can also apply the telescoping series. I think this is a telescoping series if you look at the partial fraction. But with the comparison test, the conclusion is going to be quicker. Okay, so let's start. All right, I'm going to use a direct comparison test here. So I'm going to compare this to 1 over n squared, because I can majorize the bottom of this fraction by removing plus 1 and plus 2, because they made the denominator bigger. So obviously 1 over n times n, like this ratio is always less than or equal to 1 over n times n, which is 1 over n squared. But this series is a very special series, right? P series for p equals 2, okay, which is convergent, okay, by the P series test. Okay, P series test, I know that this series is convergent. So now I'm using the direct comparison test. By the direct comparison test, since the original series is less than something that is convergent, right? So take this as like an if you want to, take this as like bn if you want to. So series an is less than or equal to series bn, and series bn is convergent, so that implies that this series is convergent. Okay, so I'm going to write here that this is a convergent series. So x equals -1 is a very good one. So I'll talk about how it will change the interval of convergence in a sec, but let's handle also x equals 1 case here. So I should have n from 0 to infinity, minus 1 to the n plus 1, n plus 2. And I said that I was going to use the alternating series test. So for that purpose, I'm going to grab the non-alternating part here. Okay. Two things, right? 1 and 2. Limit of an has to be 0, which is the case because top is 1, bottom approaches infinity. So this is 0. And an should decrease. It could be like a very small exercise for you. Look at that. An plus 1 is always less than or equal to an, which is a fact. You can check that by yourself. So all two conditions are satisfied. Okay, so this case is as well convergent. Okay, by the alternating series test. So that's an awesome news, because I can go back here that I can include the endpoints in my analysis. Okay, so I can include the endpoints in my analysis here. So the interval of convergency, the actual interval of convergency, by checking the series at the endpoints, is going to be the closed interval -1 and 1. So I can also add the equality sign here. Okay, so for this problem, I can go back and say that the interval of convergency is -1 and 1 closed interval. All right. For part C, please watch the next video.